Hello everyone. So this video is going to go over an example about mortgages to try and understand the principle of annuities in the context of a mortgage. So let me share my screen. Okay, so we now going to look at an example where a loan is borrowed and this loan is now going to be repaid at equal installments over a period of time. So let's say a person borrows $50,000 at the beginning of the year and is now supposed to pay it off in 5 equal installments at the end of each year with the interest at 15% compounding annually. Find the annual payment. Now, how do we know this is a question about annuities? Well, an amount is borrowed at the beginning of the term. And now this amount is supposed to be paid off in 5 equal installments. So annuities are also equal series of payments, and we're told that this happens over 5 payments, and the payments are made at the end of each year. Annuities can also be due at the beginning of a year, but for this class, and we're looking at examples where annuities are generally, the payments are made at the end of the year. So let's only focus on that case. And the interest is compounded at 15% annually, and we're supposed to find the value A in the annuity that we're dealing with. So now let's first try and understand how to go about computing this thing. So when we saw annuities, we looked at how to get the present value of the annuities, how to compute future value of annuities, and we have expressions for all of those. Now we need to find or have a better sense of what this present and future values are, or rather we have a we have a formula to get the present value of annuities. But do we know the present value of these annuities? Or do we know the future value of these annuities, and is that information given to us? So let's start by understanding that in a better way. So we're told that the amount borrowed is $50,000, and this borrowing happens at time 0. So time 0 is another way of just saying present. So if you think about this from the perspective of the lender, the bank, or whoever is giving you the money, at time 0, the value of the loan is 50,000. And we're told that this amount is going, and this loan has to be repaid in 5 years. It's just that the repayment scheme is in such a way that you pay it off in 5 installments. But we're told that it compounds at 15% every year. So can we calculate the final amount that is owed to the lender at the end of 5 years? Yes, we can. So the future value or the final amount of the loan is nothing but this $50,000 into 1 plus 0.15 to the power 5. Okay? Because we start off at 50,000 and it's going to grow, it's going to compound at 15% every year. And it's for 5 years. So the final amount owed is just 50,000 into 1.15 to the power 5. The present value of the loan is 50,000. Okay, now I'm just going to move this a little bit here so that not too far apart. All right. And we also know how to calculate the present value and the future value of an annuity. Now, let's write out what the present value of this annuity is going to be. Now, if I want to pay $A in the future, in 1 year from now, how much money should I invest right now? I'll do it in a different color. So if I need $A 1 year from now, I am going to need A by 1.15 to the power 1. If I need A $2 from now, 2 years from now, I need A by 1.15 squared. Similarly, 3 years from now would be 1.15 cube. 4 years from now will be 4 years from now, I would need A by 1.15 to the power 4. And then 5 years from now, A by 1.15 to the power 5. Now, what should the present value of all of these payments be equal to? Well, the present value of these payments has to be equal to the value of the loan that I borrowed at the start of the time, which is at present. So we equate the sum of these installments, we equate the sum of these present value payments. So we say A by 1.15 plus A. Okay, now instead of just writing this down as a sum of the geometric series, let me just plug it in to the formula to write the present value of an annuity. So PV is of an annuity is written as A by R times 1 minus 1 by 1 plus R power n, which in this case is going to be A by 0.15 into 1 minus 1 by 1.15 to the power 5. Okay, that's the present value of the annuity. And I'm going to now equate this to $50,000. Right? And then if I solve this expression, I'm going to be able to find what A is. And this will have the solution that A is approximately about $14,915.78. So all I did was to find the present value of the series of payments, the present value of this annuity, and I equated that to another present value that I know, the value of the loan at present, and that's $50,000. And once I plug everything into the formula, I have the value for A. Now, is there another way to go about solving this? Absolutely. And now let me just quickly show you how I do that. Now, let me hold up. Let's take this and copy and paste this. Right. Let's look at it by using another approach where we use the future value approach. Now, let's find the future value of this annuity. Well, the amount that I pay in year 1 can grow for a period of, say, 4 years and is now going to be A into 1.14. The amount paid at the end of the second year can sit in the account for another 3 years and will be A into 1.15. Yeah. We have this growing at A into 1.15 square, A into 1.15, and this will just be A. Now, if I sum all of this, the future value of the annuity, what do I equate it to? Well, I'm going to equate it to the future value of the loan. And that is nothing but 50,000 into 1.15 to the power 5. So if I sum up and write my future value of annuity, which is this, which is just A plus A times 1.15 plus A times 1.15 squared plus A times 1.15 cube plus. That's just my future value of the annuity. And that's going to be equal to the future value of the loan. And that's another way to find A. And this A should also be ending up equal to 14,915.78. That's how you calculate the monthly or the installment, the equal installment that you pay. And oftentimes, whenever you're looking at problems that involve either mortgages or something where an equated monthly installment is due, this is broadly the principle that goes behind the scenes in the calculations. Now, one thing to note about mortgages is that each payment that you're making, each installment, equal installment, is going to go towards partly repaying the principal amount of the loan, as well as partly paying the interest on the principal. Now, let's see how this works out in this example. Now, we saw that every year the equated payment is going to be 14,915. Now, what constitutes this 14,915? Well, first, one part is the interest and the other part is going to be the principal amount. No, because we have to repay both the principal as well as the interest on that principal, right? Now let's see how each installment handles this. So in the first installment, the amount of interest is going to be 15% on the overall outstanding balance. So this is 15% of 50,000. And that's 7,500. And the rest of the payment goes towards repaying the principal. And so your outstanding principal balance is now, so this amount is nothing but 50,000 minus 7,415.78. This becomes your outstanding principal balance. And in the next time period, you're going to be charged 15% of outstanding balance. You're going to be charged, let me use a different color. This is 15% of this amount. And then the rest, so that will be the interest. And then the remaining is towards the principal repayment. Again, you calculate the outstanding balance, which is just, so 42 minus 42,584 minus 8,500 gives you this 34,000. In the next period, 15% of interest is calculated on that 34,000. The rest is principal repayment, and so on and so forth until you finally pay off the complete loan at the end. Now you see how when you start off, the interest payment is the largest and principal payment is the smallest. And then over time, your interest payment becomes the smallest and the principal repayment component is the largest. So that's because at every time period, you are levying interest on, and that's because interest is being levied on the principal or the outstanding balance, and that keeps falling every time period. So this is just a detailed look at what goes on behind the scenes when you're doing mortgage calculations. So I just wanted us to walk through that example and understand how annuities as a principle are being applied to calculate these sorts of things. So the one final thing which I'll quickly review here is a concept called the internal rate of return. And this is not related to mortgages or annuities, but generally to the idea of present values. So if I have a series of, say, if I have A0, A1, and so on, up to AN, if I call them the net returns from an investment project, investment or a project, net returns meaning the benefits minus costs. Okay, let's just say. Then, what is A giving me? So, and this is A0 is at time 0, A1 is at time 1, and so on, where an AN is at time N. Okay. Now, what this A is giving me is nothing but the present value of a stream of net benefits or a stream of net returns from the project, right? Now, oftentimes you're likely to see an expression like this when you're doing cost benefit analysis and when you're trying to figure out if a particular project is more optimal, is more an optimal choice because it has higher net returns or higher profits, and so on. And internal rate of return is one concept that is used in cost benefit analysis to help us gauge or compare over different projects. And what is this internal rate of return? Internal rate of return, or IRR, is R such that the present value of net returns is 0. That is, you find R by equating this expression to 0. And solve for R. It is just R such that this expression becomes 0. So generally the choice would be to pick the project with the highest internal rate of return. So we're not going to go over this in much detail or do examples pertaining to this or understand a few more applications of internal rate of return because that's beyond the scope of this course. But I just wanted to introduce you to the vocabulary so that if you end up doing cost benefit analysis at some other course later on, you're at least familiar with where this number comes from. And with that, we wrap up our work on topics in financial economics, and we're ready to head into calculus. So thank you for staying with me for all of these videos. Good luck, and I'll see you soon.